Okay, a couple announcements for today. We are doing 6-1 day 2. Okay, you have in your possession um, the review for chapters 1, 2, and 2, 3. Okay, and along with 8. You're provided those prior to the weekend because I knew it was going to be a washout, but not necessarily that you had to get them done. But here's the process on it. 8 was given out when we did the chapter 8 test. I gave the other ones out so we could be ready for the final part A. That's this Friday. Okay? The final part A is this Friday. Now, that will be multiple choice, okay, as we're getting ready for this. The answers for those reviews are in your Schoology page on the 525 day. On the 525 day, they're sitting there in your Schoology page. So you can check that for the solutions on 1, 2, 2, 3, and 8. I think 8's been changed. I think you have pay attention to the question itself in 8. I've got to get the updated version. I've got to go through that and then repost that solution key. But aside from that, the stuff that's out there can help you. We have a quiz on 6162 on Thursday. It's on section 6.1 and 6.2. The assignment for the review is up already there for Wednesday about where things are going. Final part B reviews, all 3 of them, well 2 of them, the 4 and 5 will be provided to you on Friday, and then we will have Tuesday to go over that, and then Tuesday we will I'll give you the chapter 7 review, and then Wednesday and Thursday working on that with Friday the chapter 4, 5, and 7 test. Okay. Yeah.
Are the tests like combined in the grade book, or will they be like?
They will be put together. And the reason we're doing it this way, twofold. One, you can focus in on one. You don't have to get ready for all of them at one time. 2, I think more people will be doing tests later. I mean, I'm hoping that that'll be the case. And just want to make sure that you get a longer time to prep for that sine, cosine, tangent stuff. Okay. The same material that was provided to you, the cheat sheets for the time that we took the sine, cosine, tangent tests, will be provided again. And that, Mr. Foss.
Is there like a certain weight on those tests? Or?
You know, the beauty about how we're doing it for you is that each test has got the same percent. So the chapter P test has the same percent as your final test. If this was a course that was actual college, it would be probably 20% for the first part of the semester, 20% for the second part, 40% for the third part, and then the remainder would have been homework. So 20% homework, 80% test, but 50% for the final. I will not be weighting it that way. They're evenly weighted that way for us, which is a change. And remember, we're testing way more often than you would have on campus, okay, which is a benefit because tests have less points and you can afford to have a bad test and still come back from it versus 20%, 20%, 50%, the way they'd be doing it on campus. Any others? Okay. I think with that said, today we're looking at talking about velocity, talking about speed, applying our vectors. What we're looking at really, we're going to be using these vectors, absolute value v cosine theta and sine of theta, working on our vectors with this stuff in mind. Okay. Keep in mind we're thinking reference angle, the angle to the reference of the x-axis as we step through these. So in this DC-10 jet aircraft is flying a bearing of 65 degrees at 500 miles per hour. So we got this stuff going on, but remember, its reference angle, the angle from our axis is 25 degrees, and that's where we're taking our vector, okay, from. We're not going with from north on these. Find the component form of the velocity of the airplane. Recall that the bearing is the angle that the line of travel makes with due north measuring clockwise, okay, as we go. But when we're doing this one, I'm going to get my figures up here. when we're getting this collected, keep in mind, we're going to be working with that 25 degrees because that's the reference angle. So I have the bearing of 65. And as I'm going through here, as I've got it, so I've got a velocity. And do I want to write it that way? No, I've already written it that way. I get my vector, and I'm looking at my absolute value of my velocity, cosine of theta, sine of theta. Okay. As we're going through, keep in mind, I've been given the absolute value of velocity already because my jet is traveling how fast? 500 miles an hour, so that's my absolute value. So I've got 500 as I'm going. Cosine of, I want to be working with my reference angle, 25 degrees. Okay, and 500 sine of my reference angle, 25 degrees again, as I'm stepping through. Now, I want to be able to pull up my calculator here, and they've asked me to come up with the component form, and I'm using the formula, really, if you want to look at it. This is my component form of my vector when I'm given my absolute value of velocity, my magnitude, which is speed in this case, and the angle that it has for the reference angle here. So when I pop this in my calculator, I'm going to pop out 453.154 and 211.309. And this is the component form of my vector. As I'm looking at, and we're talking about the airplane's path, off of bearing. So I've got the horizontal and vertical component forms there if I wanted to talk about AI and BJ, if I want to look at them separately. Any questions on being able to pull those up and be able to work with the reference angle? Doing okay? Now remember, the next one's a little bit more involved. I didn't have anything like we were in still air. I didn't have anything messing with the my air travel. I didn't have another vector of wind coming in here. This was just straightforward. Okay, finding the component of the plane. Okay, are there any follow-up questions with it? Now, when we're doing example 8, we're talking about the component forms. I've got two different vectors here. I've got AC coming off here, okay, and that's there. And I got AB coming in here, okay, and that's down there. But I have a resultant vector. So the two vectors are going to combine, and I'm going to have my first term, my A terms, and my B terms add together for the resultant. And I want to be able to go due south, okay? So that's what we're going to be doing, okay? So the pilot, Megan McCarty's flight plan has her leaving San Francisco International Airport and flying a Boeing 727 due east. Right now, I gave you the fact that it's due east, okay, and that's our resulting vector. So these two vectors, AC plus AB, should end up going due east. There is a 65-mile-an-hour wind with a bearing of 60 degrees, okay, coming in. Remember, this vector we were working on yesterday, this vector can be passed over here to make sure that we're going due east. Eventually, we're going to add one vector to the next, adding the two to see what they combine to go due east. Remember, that's 0 degrees as a reference angle. Okay. Find the compass heading McCarty should follow and determine what the airplane's ground speed will be, assuming that its speed with no wind is 450 miles per hour. Okay. So the first thing I've got to be doing, I've got to look at my AC. So I've got AC coming on here, and I'm just going to be talking about my vector AC and my component form of that vector. So remember, we did it with sine and cosine, and I got 65, and maybe I'll just get that written first before I start writing it down. So I'm working with this vector. Okay, and as I set this up, and I'm talking about my wind speed, AC, we'll talk about that being AC, I have my vector AC coming up at 65 miles an hour, cosine of 60, and cosine of 40. 30, excuse me, because it's my reference angle here. Cosine of 30, and I got 65 miles sine of 30. You okay with my AC? Okay, you okay with where we're coming from? Now, remember, I'm working here, inside here, and I'm going to work with my reference angles. Now, the next one I'm going to be working with is the fact that I got AB. Now, there's some information of AB I don't have yet, and we're going to solve for those. Okay, but I want to make sure that we do our setup all right. So we're going to assume that our plane is going to travel at 450 miles an hour. Okay, so we got AB, plane's going to be traveling 450 miles an hour. I don't know theta yet, the plane's flight. I know the resulting spot, it's going to go due east, but I don't know what the angle is, and that's what we're going to find. So I'm looking at this at 450 cosine of theta, because I don't know what my final is yet, but I will. And I got 450 sine of theta. Okay, now keep in mind as we're setting this up, I got my A and my B and my AD. Right now, AD is a vector as I'm going through here, and I don't know my velocity yet because the wind might push me, the wind might pull me, whatever, it might help. But I've got this cosine, and I don't know my angle yet. Well, or do I? What's my theta here for my final destination? 0. So I've got this here, so that's going to be 0, and I've got this one, sine of theta, which is again 0. Okay, which is really nice because I'm just really looking at my AD being absolute value of my velocity, and this, my sine, is going to be 0, so that's my vector. Well, I'm going to use that idea to help me out here, because that's just gave me an easier step through for my problem. Because if I consider my sine values, these two sine values should be combined to be 0. Okay, so I'm going to use that to find my theta. And the theta that we're finding is the direction my plane's got to fly kind of into the wind to keep myself going due south or due east. Okay, so I'm looking at this and I go, well, you know, if I add these, I got 450. And remember, the resultant is just adding your A's and B's together. I'm just choosing to add the B's right now because I know the B answer is 0, and that'll help me out. So I know 450. And well, I'll just do it in order, 65. No, 65 sine of 30 plus my 450 sine of 0, no, excuse me, sine of theta, because we got to find that, is equal to 0. Okay, are you okay with the relationship that's been set up? Now I just solve for theta, okay, which is kind of nice. I got my 450, I'm going to go over to the side, my 65 sine of 30, excuse me, and I've got, so 450 sine of theta is equal to negative 65 sine of 30. I'm going to divide by 450 and then take the inverse sine. And so I've got to check my calculator because I'm going to say, hey, you know, theta is equal to the inverse sine of negative 65 sine of 30 all over 450 as I pop that in. So I'm finding my theta. Yeah.
So did you get the for the AD, the fact that it's just the velocity at 0? Did you get that because cosine of 0 is 1?
Yes. Correct. Correct. And if the problem opened itself up to be very kind to us, you know, when we were doing this, and I'm choosing to find the theta that the plane's got to travel by, because if I did my cosines, I wouldn't have the velocity it's traveling at or the theta. Once I find theta, I can plug it in and find velocity. Okay, does that help? Okay, thank you for the clarification, Clem. Okay, so now, hopefully, let me get this in here. I've got inverse sine of negative 65 sine of 30 divided by 450. And we got negative 4.142. Okay, I mean, I rounded it to the thousandth, but there's still stuff in my calculator that I'm going to use with ants. But remember, that makes sense because up here, for traveling due south, that's 0, and our plane's making a correction that's below 0, which is negative 4.42 degrees. Okay, so that's currently the theta for my airplane as I'm going through on my chart. Are there any questions why it's negative 4 point? We're doing okay there? Now, when I'm looking at sine, I'm done. I go up to cosine, and let me open that up a little bit so you guys can see the cosine relationship there. So I've got my cosine is going to be 65 for my AD. I'm totally saying the AD, the absolute value here, is going to be equal to this value plus this value when I set those up. Because the resultant vectors, I'm adding AC and AB to get AD. And AD is the absolute value of V, and that is made up of 65 cosine of 30 plus 450 cosine theta. So here I've got 65 cos of 30 plus 450. Now keep in mind, we just found theta, negative 4.142. Okay, because it fits so well there. Let's see if I can get it a little smaller so you guys can see what I'm doing. You okay with why I'm putting it in there? I'm going to solve for the velocity I have to travel with my plane at that angle to buck the wind or go with it to go due east. Okay? So again, I grab my calculator and I'm looking at 650, or 65, excuse me, cosine of 30. Don't forget to close your right parenthesis on that. Plus 450 cosine of, I'm just going to use my ants key and come up with 505. So I've got 505.117 miles per hour. Okay, that's how that's how fast my plane's got to travel on that angle of negative 4.112. Okay, that's the speed it's going to travel because it's getting pushed. Okay, but now I don't quite have my bearing because remember bearing is from north. I do have information that's going to help me with that. Okay, because my flight plan bearing happens from 90 degrees, not our original position. Our standard position is due east, and I have used that for this problem, and now we're going to go to bearing from north, which is 90 plus 4.142. Okay, so this is my speed of plane. It's right there. And my last piece is my bearing, and I'm going to add 90 plus the absolute value because it's below the axis, 4.142, and it's going to give me 94.142 degrees. This is my bearing of plane, and this is the bearing from north of flight of plane. Say from north, flight of plane. Let's put it that way. The of was ahead of me. Any questions about those two solutions as I step through it? Are you okay why I'm adding 90, why I'm adding that 4.142 for the bearing? Are you okay with what I did with getting my velocity of how fast the plane's going to go on that angle? Okay. Got 2 left. Let's look at the first one. In this first one, I already know that my x value, because it's up and down, is going to be 0. We're going to talk about my y. I'm looking at the weight of a box, the force of 30 pounds to keep the box in figure 6.15 from sliding down the ramp. Okay. Now, if I'm going to try to keep this from sliding down the ramp, the incline's at 20 degrees, find the weight of the box. Well, here on this side, we got the force of gravity. AB is a component of AC, and I'm talking about AB. Where's my AB? AB coming down. For AC, coming that way, that holds the box against the surface of the ramp, and the component AD and CB, they're equal. So I'm talking about AD and AB, or BC, excuse me, these are the same. These are my 30, these are 30 pounds going to be sliding. That's a 30 pounds as I'm talking about this. Okay, that tends to push the box down the ramp. Okay, but it's right now at 30 pounds, but it's not moving. Okay, we know that that takes 30 pounds to hold it in place. Well, if I'm talking about the actual weight of the box, the hypotenuse there, I've got an opposite hypotenuse setup. If I'm looking at sine of my 20 degrees, and I'm looking at the idea of BC over omega, where omega is my weight of my box, my actual weight of the box, they want me to find the actual weight. So I've got this set up, and they told me that BC was equal to 30 in the information provided in the problem. So I'm going to plug that in. I suppose I should have plugged it in initially. And now I'm going to multiply by W, divide by sine, so omega is equal to 30 over the sine of 20. Okay, the actual weight of the box, because sliding the box is actually lighter, it takes less force than actually lifting the box. Okay, so if I go there, and I've got 30 divided by sine of 20, and we got 87.71, and omega is actually 87.714. So the box is 87.714 pounds. Okay, when it's on that ramp. Now, if I increase the size of the ramp, okay, if the ramp is like 20 degrees, now we double it. What's going to happen with the weight of the box? If I keep the pressure that holds it in place the same, will the weight of the box go up or decrease? For the pressure to hold it the same would be 30 pounds. Speculation. Remember, if I'm in an inclined plane, if I'm doing any type of lifts, if I'm pulling myself at a lower incline, it's easier. As I get to vertical, it becomes more difficult, like a pull-up. Okay, I could cut my weight in half with 45 degrees. As I increase the ramp's incline, but keep my holding power at 30, the weight of the box will decrease because it's not as heavy. Okay, and I'm not saying the weight of the box will decrease in this problem. It's just that if I still have my holding power, or the amount of pressure necessary to hold it, the box would have to be less weight and able to hold it on the ramp at that angle. Okay, does that make sense? So if I want to push something up an incline and it's heavy, I want to make the incline as long as possible. If I try to make it really jetted up and it's really fast, it'll be harder to push up the incline. So you'll need more friends and pizza, okay, because you got to call them up and say, hey, I want to move something, so I've got pizza for us after we're done. Okay, so just keep that in mind as we're going. Questions about the force problem? And I want to talk to Anderson about how we do it and physics does it, so I know sometimes it's a little change. Our last one here is about vector components, form again. This is all about a salmon swimming upstream and at a particular point of the swim, okay? During one part of its migration, a salmon is swimming at 6 miles per hour, okay? So AC, and if the salmon's just going all by itself, okay? And let's just assume this is north, So we got the y-axis, x-axis here to make it simpler for us. If I'm looking at this, I'm really going 6. If I'm a salmon, I can go 6 miles an hour in nice, steady, clean, still water. So that's AC, okay? That's vector AC, 0, 6. Okay. Now I want to talk about the current. The current's fighting us. It's going in that direction. Our current is AB. This B should be right here, so we can talk about it here and here. Our current is AB, and that's fighting us. Okay, we got to fight that. We got to overcome that to actually get up the river and do our thing as salmon. During one part of its migration, a salmon is swimming at 6 miles per hour, and the current is flowing downstream at 3 miles per hour at an angle of 7 degrees. But remember, that angle of 7 degrees, excuse me, I wasn't supposed to do that. That was kind of fun. But that angle of 7 degrees is right here, so that's 7 right there. The reference angle, are you okay with that being negative 83? I mean, it's 83, but we're really talking from our standard position is negative 83 degrees. So that's our reference angle in this problem. So I know that my AB vector, and remember, I've got the absolute value of my magnitude, my speed at which I'm swimming upstream, that the stream is flowing at me, I should say, is 3. But I got a cosine of negative 83, and I've got a sine of also negative 83. So that's my AB. Now, we're going to be able to take AB and AC, okay, because that's going to be our speed our salmon can run at, of 0, 6, and we're going to find our resultant. So we're going to take AB plus AC, and we're going to get CB, or that resulting vector, because we're going to add the two together, okay? So as we get this going, that's our first thing, to find our component form of the vector. After we do that, we're asked here, how fast is the salmon swimming upstream? We're not asked about its direction, we're asked about speed. And we take the resultant of the vector after we add the forces together that are acting on our salmon, not just the stuff the salmon's acting on, but the stream, and we're able to find how fast the salmon's traveling in the stream. So when I take my AB, my AB, this stuff, becomes, I'll shortcut it for us, I already did the figures here, 0.366 and negative 2.978 in our calculator. That should be our AB result right there, okay? And I'm going to add those to 0.6. So I've got 0.366 and negative 2.978 plus 0.6. And that's going to be my CB. Well, it's really nice. The first one's 0.366. The second one is 6 plus negative 2, and that's going to combine. They're going to be 3.022. Now that's my CB. I suppose I should make sure I put my ray over that. Now, to get my magnitude, I'm going to take the absolute value of them. You know, I'm going to put them in the Pythagorean theorem with that A and B. So I'm going to take CB, and that's going to equal 0.366 squared plus 3.022 squared. And my result here becomes 3.094, and that's miles per hour upstream. That's the speed of my salmon. That's relative to the bank of the stream. The salmon believes it's actually swimming 6 miles per hour, okay? But if I'm on the bank with a radar, well, it's speeding. It's 3 miles an hour. It's going over the speed limit, okay? But it's just really a lot of fun to watch them swim up and jump over dams and that. But that's the information I've got going for the speed of salmon. Are there any follow-ups with that at all? Keep in mind what's going on, what things are on the horizon for us as we're going. If you have questions, I'm here tonight and tomorrow morning and tomorrow night. I'm here Wednesday, Thursday, Friday by appointment, so I can work with some folks that need more assistance. Okay? Thanks for your time, and keep it going, keep things getting done.